Yep. So the group has been set up recently. Socialize and have some reflection. Then we have a very effective moment. Then we will have some acknowledgement to make, and we will introduce and then after that we have to talk about math, followed by questions and answers. And after that we go to wells. So standard is buying the test day for everyone here, and then we are looking to follow up on things. Okay, for our safety moment, it is really about being aware of our situation and being mindful and ready for different situations that we may have. So Matt, if you'd love to tell us about and all of that.
Okay, sure. So in the event of emergency, please, there's an exit behind us. We're going to exit through the building, kind of past the elevators and into an evacuation area in the car park where many of you came through. In an earthquake, please hold on if you can maybe squeeze under a desk and just stay where we are. We will we'll gather you and lead you to safety.
Yeah. So I'd like to acknowledge Ika, hosting us. I'm really thankful to and for the whole team. And also for the people here, every one of you, as well as the people that are joining us online and the people that requested a link to that recorded video. Of course, thanks to Matt for preparing this talk, and that will deliver shortly. Yeah, Environment Canterbury, Stantec, and IAH New Zealand Hydrogeology were all helpful in arranging this event. And we are really looking for volunteers for the following talk. This is our very first talk. So everyone here or online, please consider volunteering to help us. We have not invited only people from the Geoscience Society, but we extend that invitation to everyone else, because we thought that there is quite a big value in this. We will continue to do that. Every 2 months, we have one such talk, and on the alternative month, we will have a special meeting for the special interest group that is open only to the members of the Geoscience Society. Yeah.
Sure. Can you stand a bit closer to the mic, please?
Yeah, and of course, we welcome any sponsorship or any kind of contribution that any organization can provide for us for the good of the hydrogeological community. So just a quick idea about the SIG. We know that 80% of our fresh water lives under the ground, and this is why hydrogeology and groundwater are quite important. And to take care of this resource, we require a vast amount of expertise and different specializations. And part of that will come from the geological community, because after all, this is a hydrogeological science, which is really combines hydro with the geology. Yep. And the objectives of the SIG that has just been organized recently is to stimulate interest and knowledge of the hydrogeology amongst geologists, raise the profile of geologists in the groundwater area, and also to establish and strengthen ties. So the setup of the SIG, it's been established just recently in May, and the membership is open to Geoscience Society of New Zealand members only, but everyone is welcome to the talks and such events. I am the convener, Hisham Zarour at stantec.com for this group, and I welcome membership, and I look forward to seeing more and more active people joining us. Yeah. So now we will move to Matt's talk, and if you have any questions today, you'll have the chance to ask Matt after he finishes. But also, this is Matt's email, and that's my email, and you can forward your queries to both of us. Thank you, Matt.
Cool. Thank you.
If you'd like to start with an introduction.
Sure. Tēnā koutou katoa. Noa tāmaki nui arua aho, ko Matt Dodson. Ki kamahi aiho, ki te koni hira aiau ki Waiteha. Nō reina, tēnā koutou, tēnā koutou, tēnā koutou. Welcome everyone. What a great turnout today. First I'd like to thank Hisham for inviting me to this first ever Hydrogeology Special Interest Group talk. It's a real pleasure and honour to be here today. And we're going to get really annoyed by that noise, I think. But it's great to see the amount of interest this particular talk has generated, and it's great to see you all today. I just want to reiterate some of the points that Hisham made. When we started talking about structuring this talk, we talked about giving people a sense of what we do as hydrogeologists in the broader sense, how we interact with the geoscience community, but also I think central to it is really emphasising the importance of geology, of geoscience in our profession, and how much we actually use it day to day. And that's really my aim today, is to give a bit of a plug towards geology and hydrogeology, and to hopefully just demonstrate how critical it is to my day-to-day kind of work. Actually, I'm going to go back a little bit. Because we are going through MS Teams and in person, you're going to hear those beep, 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 and that's notifications from people online. For those people online, I can't really see what you're saying. I can't see your messages as such. So can you please just mute your microphones? And if you write questions in at the end of this talk, we'll try to get to some of them. And if I can't, then we will try to capture those and we'll respond later on. So a bit about me. So I've got a background in geology from the University of Canterbury. I've got a BSc and a MSc, and I've spent about 10 years in regional council, working in various areas, mostly in Canterbury, but a little bit in Hawke's Bay. And I've had a range of roles, studying as a summer student, being a master's student supported by Environment Canterbury, been in the field team, a scientist, a tech lead, and now as a team leader. And through those experiences, I've had the opportunity to engage in a lot of really interesting projects, and they range from participating in a community-led planning process through to doing investigations around groundwater quality and quantity, reporting and investigations and project management. So I'm not going to dwell on that. I'm going to go directly into it. Hopefully. So today what I'm going to try to cover is what do we do as hydrogeologists? And I'm going to try to take it as broad as possible and take in the broader hydrogeological world. I'm going to try to answer the question, how important is geological information to hydrogeologists? And I'm going to talk about our needs of the wider community, and I'm going to use that by talking about a couple of examples of projects that I've been involved in over the last few years. And then at the end, I'm going to have a little bit of a pitch around groundwater visibility and resource management. So to start it off, what do we do? What do hydrogeologists do? So there's an image I took off Google Earth. Many of you would be aware of this. It's the water cycle. If you really want to read all the captions, it goes from evaporation all the way around to infiltration. But essentially, as hydrogeologists, the core thing we do is look at how water and what moves with water kind of moves through rock. It's pretty simple, right? But our area really is looking at the subsurface and how water and all those things that move with it, chemical parameters or biological life or heat or all those types of things move. That's the commonality between us all. But when I start to think about what do we do actually, and I started drawing on resources from the International Association of Hydrogeologists website and others, common words kind of came up, and it often started with the words investigate, design, remediate, construct, and measure. So those words are up top, and we'll put them in front of these other types of things. So what do we do? I think it's, essentially we investigate, remediate, and measure kind of gravitational and also hydrothermal kind of systems. And I think as someone who's worked in kind of the cold water field, it's really, I think I need to acknowledge that there is this hydrothermal system. It is very important, and lots of people rely on it for different values. What do? We install bores, we design, we construct, and we measure bores, wells, piezometers. When people think of groundwater scientists, I think that's probably the first thing that that jumps into our mind. What else do we do? Monitoring networks, so design, construct, and measure monitoring networks, whether that's for spatial environment monitoring or monitoring around a mining pit or for whatever other reasons. Water supplies, obviously. So a lot of hydrogeologists are involved in designing and constructing water supplies, and I mean in a more broader sense in terms of irrigation bores, public supply bores, or even a hydrothermal kind of development bore. Dewatering schemes. As hydrogeologists, we get brought in to draw water away from excavations, and the three classic examples that jump into my mind are around mining, through tunnels, or through when there's an earthquake in Christchurch and we need to rebuild and dig into the ground. Contaminated land, not so much in New Zealand, but particularly overseas. There's a lot of work around contaminated sites and their impact on the groundwater system beneath. The field that I'm most familiar with, and that's environmental impacts, looking at evaluating, assessing, auditing assessments around what the actual impact of certain activities have on the groundwater system. And the last one up there I've put in managed aquifer recharge. I couldn't pick a more generic term for it, but there is a group of people who put in these types of schemes to remediate where groundwater storage or both base flows and streams have been declining for whatever reason, and they go in and put in deliberate, engineered kind of structures to remediate. But when you think about across these kind of tasks, I guess, it goes across all the types of sectors, from energy and mining, construction, environmental, into three waters and infrastructure. And I guess if we kind of think about engineering geologists and your geotechnical engineers, there's this crossover into those fields also. So, what do we do? When I started thinking about this, I also started thinking about the skills we employ, the people and their skills, their backgrounds, and the disciplines that they bring. And as a hydrogeologist, we obviously can't kind of be masters of all this thing, but we need to be confident of them and also bring in that expertise from other fields. And I've deliberately color-coded these, and I'll talk about that a little bit later. But of course, there's the core skills around, geology, geochemistry, geophysics, the things that kind of come to mind. But I think we need to be mindful of those other disciplines, mathematics and statistics. I'm thinking specifically around groundwater modeling and the like. Something that's kind of coming into the fore now is data management and computer science, and particularly managing, manipulating, and interrogating large data sets, particularly with programming languages, and kind of getting into the back and using Python and your R to kind of understand those data sets. But I also think about, I guess those are your core kind of science skills, but there's other things that you need to be aware of or blur, or our jobs kind of blur into, and things like project management, being able to kind of effectively run a project, is really critical. Things like communication, and making sure that we can talk to people via different, whether it's in person or electronically or via reports, making sure that we can actually tell others what we do and the findings that we have. And I guess there's a whole pocket down here that around economics and social science and indigenous knowledge and policy. So there is this grey area where the hydrogeologist, the pure hydrogeologist, needs to kind of mix with the broader kind of broader world, I guess. When I was kind of looking at this thing, I was also thinking about different lenses you might want to kind of look at this. So, my background is from regional councils, and one of the things that I need to be aware of is resource management documents and policy frameworks, and being able to interact with policy and decision makers. That's something that as a hydrogeologist I need to do. But if you're a consultant, you want to be able to bid for work and to successfully get that work, or to manage your clients, or as a CRI or academic, you might want to build up relationships with your stakeholders and your funding organisations and make sure that you publish. So that was my attempt, really, to give an understanding of the breadth and width of hydrogeology. So how important is geology to hydrogeologists? Well, it's critical. It's central to everything that we do. And, you see it, right in the definition of aquifer. This is not quite, there are many definitions of an aquifer out there, but they all kind of have this similar kind of wording. It talks about, a soil or a sediment or a rock which has and contains or transmits groundwater for some purpose. But central to that is understanding the physical properties of that soil and that sediment. I put up an image here of the cross section through Christchurch, which we always kind of throw out, just to kind of reinforce around how integral that geological framework is. When we, in my opinion, one of the first things and most critical things we've got to do whenever we start a project or a new piece of work is to start thinking about a conceptual model, and thinking about that framework and so that we can understand what we're looking at and interrogating. And we do this for a couple of reasons. We have imperfect information. We don't have data all around. So we are mapping out what we think that system is, so that we can get a sense of that system, but also so that we can test it as we go through our projects. I deliberately chose these two kind of in-member conceptual models. On here is Bruce Hunt analytical, it's a schematic explaining his 1999 stream depletion analytical model. And then there's a 3D representation by a colleague of mine, Philippa Asian Earl of South Canterbury. And for those that can't read it, Otaya River's down this end towards the word conceptual model, and on the other end is the Whakatoki River. And I chose these deliberately because they show some contrast, but they also give us a sense of the importance of geology. So I guess in terms of contrast, we have Bruce Hunt's model here, which is a 1D analytical solution, versus Philippa's 3D representation of South Canterbury. In terms of scale, you know, this conceptual model is looking at something quite localized, the effect of pumping a well on a nearby stream versus a sub-regional scale model. In terms of time lag, or the time scale we're talking about, you know, when we do a stream depletion analysis on an individual bore, we're talking about 7 to 150 days. When we're using these conceptual models, we're thinking about the cumulative effects and those long-term factors that affect the system. So there's both temporal and spatial kind of differences. But the similarity between these two is that you need to build these conceptual models from the information that you have at hand. And this is where we start kind of talking about the information that we draw, particularly from the wider geoscience society or profession. And I've put up some examples here. On the left, you've got the bore log done by a driller in Upper Whakatoki, and obviously these gives us point information around the geology of that area. You string a few of them together and you start building up an idea of the cross-section across an area, and you start building up an understanding of how that geology varies through that time space. Up top, we have a ground penetrating radar line. And I'm using this example of, you know, the ability to gather information about the subsurface from geophysical methods and be able to incorporate that into our conceptual models. Obviously, maps. So this is a picture from a QMap, but it could equally be SMAP put out by Landcare or any other map that. And of course, the last thing that we commonly use is observations. So going out, having a look at the geology, the strata in the field, and tying all these pieces of information in to develop what we call a conceptual model. Right. So what I'm going to do now is kind of take you through a couple of examples of a couple of projects that I've been personally involved, where I think kind of highlights the importance of geological information and how the stuff that, or the information that other people have produced has really benefited myself and Environment Canterbury. And the two examples I'm going to talk about is around the Marahi Downs. I'm going to be talking about the tectonic impacts that you can see on surface and groundwater. And then a project down south where we are looking at loess soils and their impact on recharge. So in terms of a bit of a tectonic setting, the image on the left-hand side of the screen is from Yard Pettinger, and it gives us a sense of New Zealand and the broader kind of setting. Many of us know that in the north, New Zealand is sitting across the plate boundary between the Pacific and the Australian plate, and in the north, the Pacific plate is diving under the Australian plate, and vice versa to the south of the South Island. The Alpine Fault is connecting these two systems, and then between the top of the South Island, you've got a series of fault zones that connect across. The Mobile Fault Zone is to the north, and these fault systems young towards the south. And we're going to have a quick look at the Porter's Pass Amberley Fault System, or part of it, or near it, in an area just north of here. On the map on the left-hand side gives you a sense of the area. We are Christchurch, and between us is Waimakariri and the Ashley. The blue lines are obviously river, and the red and orange lines are active and inactive faults. If we zoom in a little bit closer, and apologies for, I'll be better on that side. So we're zooming into this particular area. And I'll just move on to the next slide. So the previous slide was just meant to give you a sense of where it was. This is the same map, the same location. What I've drawn in here is the rivers, so the Ashley River, Rakahuri, and the Cuss River. In the background, I've got the Q map, and I've used the unit signs to indicate the geology. The little blue dots are springs and where they're located. So this particular part of the world, there's been quite a lot of work done. The University of Canterbury, I think they've called it the North Canterbury Tectonic. I can't remember the name of it, but they've done master students, honours students, and PhDs throughout this area. I think Hugh Conan mapped the faults to the north in about 1992. Richard Sissons and some others mapped some faults kind of just off the page in Loburn. And there was a couple of master students that did tectonic geomorphology, structural geology, and I think some geophysics on these two large features that are marked MUV and the PLK. Not only Canterbury, but Geoscience and their predecessors have done quite a lot of work in this area, mapping faults and getting us an understanding of the geology of the area. And I guess lastly, in about 2000, there was a group called Indo-Pacific Energy who went out and did some oil exploration around this area. And I'll show you some images in the next slide. But they drilled a deep bore, about 1,500 meters deep, and then a whole series of seismic lines. And they're obviously looking for oil, petroleum at depth. I guess what I'm trying to get through with this image is that the location of those springs relative to those fault lines. And to me, this is not a coincidence. Some early kind of land vegetation mapping that was done by a guy called Dodson in 1961 kind of showed this area was wetland. If you look there now, it's farmland, but probably most of it's been drained. When you look at the flow and loss patterns of the Cuss River, up the top end, and sorry, I don't have a pointer, but kind of to the left of your image, where this Cuss River starts, it has permanent flow. As it comes down, it starts drying up, and where those springs are located, you start getting more permanent flow. So what, in my mind, what is happening here is you're getting uplift of those sediments, you're getting a contrast of the hydraulic conductivities, and water is kind of flowing to the surface. And the fact it's doing here, it's influencing both the groundwater system, which is flowing from your left towards the right, towards the Maraki Downs, and also the surface water system itself. So the image on the top left is the seismic lines that Indo-Pacific Energy undertake or did. And I love that map. You can really see the relief of the area, and you can kind of see how much uplift and changes in landscape have occurred. In 2016, we asked Mahoney and some others to do a piece of work for us where we did some shallow seismic across some of those lines to give us a better sense of that basin. On the right-hand side is a seismic line. This one is ECAN SR01, and you can see where it's mapped on the other side. You might be able to just see a marker saying Optic Road. So that is the end closest to the Starvation Hill. And this end here is going towards Ashley River, Rakahuri. So they've drawn in some pretty rudimentary interpretation. You can, sorry, this is in two-way time. And I'll give you some depths later. But so they've done some rudimentary interpretation. You can see how that faulting has changed the shape of that basin. So they've interpreted quaternary gravels, and that depth is somewhere between about 210 and 230 meters below ground surface. And then a Kowai gravel down about somewhere between about 470 and 420 meters below ground surface. You can see what is a fault, and if I squint, I'm pretty sure it's going all the way to this or near the surface, and I'm sending some reflectors in that chip layer bending over. It shows the impact of faulting on the system, and in my opinion, it probably is going to have an effect on where that groundwater is going to flow. So, in my mind, this is a pretty obvious tectonic influence on surface water and groundwater, and it was the reason I kind of showed it. It's not groundbreaking. It's not you know, a novel study, but it does show that clear, in my view, a clear impact of that tectonic structures on the flow. But it also points out to all the data sets that we used in construction of that study, and how we might use it to improve our understanding of that system. I do think it would be actually quite a good MSc student project to look at the groundwater system, but I'm just going to throw that out there. I'm going to move into the second of my examples, and this is around LERS and groundwater recharge. In the following slides, I'm going to show some maps, but generally, LERS covers tens of thousands of hectares across Canterbury. In my opinion, it's quite poorly understood, and it behaves very differently from other soils, particularly on the plains. And it behaves differently in that it encourages runoff as opposed to infiltration. So the map on the left is from a colleague of mine, Paulson, in 2013. The image is probably S-maps, and we're looking at Freshwater extents and late Pliocene LERS extents. If you use different criteria, you'll probably get a slightly different map, but it does show that there is widespread distribution of these kind of soils throughout Canterbury. For those that you don't know, it is a wind-blown silt or dust. Sorry, I'm just going to grab my notes. It's produced in specific periods, mainly when rivers are grading, and it's preserved in surfaces above active river channels. And people have used it as an indicator of surface age and of paleoclimates. And they can be really thick, and I'll show you an image of a place down Timaru. And the soil properties don't match some of the soil moisture modelling that we've done previously to estimate recharge. So the stuff that David Scott did in 2004 assumed no runoff, and it doesn't apply on these types of soils because of their physical properties and because of topography, as we'll see. And I guess the other point to make is that within these soils, they have this thing called a fragipan, and that's at depth. It is a dense layer that potentially has the ability to inhibit infiltration through it. So on the left-hand side is an image of a sequence of LERS to give you a sense of how thick it might be. I don't know how thick that is, but it's probably in about 10 meters. And then on the right-hand side is a kind of conceptual model from Low & Co that I think is really a useful way to think of how these soils kind of developed and the impact on groundwater recharge. So I'm going to start from the top and talk my way down. On the top there, we have a flat alluvial surface. And at some period, there must be a LERS accumulating, and it forms on that surface. And then at some other time period afterwards, that LERS either stops accumulating or the rate of accumulation decreases, and then you get some erosion to that surface. You then get another period where that LERS starts accumulating and it mantles the topography underneath, and so on and so forth. And then eventually you might have 3 layers. And I think the interesting thing about these 3 layers is that, bearing in mind that there'll be a fragipan, and above that we'll have a permeable layer, is that it gives you a sense of the geometry of these layers, but also potentially where the groundwater might flow, or rather, if instead of infiltrating directly through, like you might imagine a typical soil out on the plains, actually it might fall on those crests, either run off directly down to the valley, or infiltrate into your A horizon and then go down. I think it's a really useful kind of way to think about how these soils form and their impact on the recharge. So at Environment Canterbury, we've been kind of battling these soils for probably 20 years and trying to get an understanding of how much water actually penetrates them and gets into groundwater. We do know that there must be some recharge through these soils somewhere, but how much is proven to be really quite tricky. So one of the things that we decided to do a couple of years ago was to actually go out, find a small scale site, instrument the heck out of it, and just measure all the parts of the water balance that we could. So we ended up identifying this farm near Otago. It's a small paddock. It's about 4.5 hectares. There is a single centre pivot that covers this whole valley. It's covered in loess. It's a dairy farm, and for the study, it's quite critical that it's in pasture. We don't have crop rotations or the like. And it's also a very reliable, or the farmer has a very reliable source of irrigation. So this project's actually been done in collaboration with some partners, and from Lincoln, NIWA, Plant and Food, Earth and Environmental Science. So this image on the bottom left-hand corner was in the slide previous to the one, but I also wanted to just show you some photos of the site just to accentuate the topography of this area. Like if you were to look at a map view of the site, you probably think that there's a little bit of undulations, but when you kind of get to there and you see photos, you see there's actually quite a lot of relief, and you can imagine how, if there was a bit of rainfall, how quickly it might run off down into that stream or into the valley bottom and out towards the trees. So for this particular site, we got a drone and ran some high-res topographic information. We have some soil pits. Those soil pits are just to the left of those tracks that you kind of see in the image there. And I'll show you an image of those pits next slide. And we took a whole series of physical measurements from them. And we've done a whole series of hand augers, piezometers, and soil descriptions. And you can kind of see on the right-hand side near the trees, might see the outline of a structure, and that's a surface wear, so we can measure the amount of water coming out. So this is a picture of each of those three pits that we put in place. I tried to align the photos so that you can get a sense of where they are in the hill slope. So the one furthest up is at the top. The one on the furthest left is near the valley floor. I'm not going to talk too much about these images, but there's some obvious stuff that jumps out even to me, not as a soil scientist. So the brown stuff, the A horizon, thickens as it goes towards the valley floor. You get this grey veins, which your macropores probably caused by tree roots or other kind of features, and they are kind of reduced grey stuff. And if you put your finger in them, there is actually water kind of flowing through them. I do love these photos, but I'm going to move on. So this is an image of that field site, just to give you a sense of the instrumentation in place. So the red line is the approximate catchment boundary. There's a climate station that NIWA put in out of the site, out of the centre pivots. It gives us a sense of the actual rainfall in the area and the ET. There's a centre pivot, and on that we've got a GPS. Those X's and Y's are the locations or approximate locations of soil moisture probes, and we've got two types in there. And on the outfall or to the exit of that valley, we have a surface weir and a subsurface weir. And the subsurface weir is basically a trench where we're capturing all the water that goes in the upper part of that soil profile. So we're basically trying to measure all the parts of the water balance that we can, with the hope of solving for the residual, which will be groundwater recharge. As we go through this study, it becomes clearer and clearer that the likelihood that there's a large amount of recharge going through these soils is unlikely. We had a sonic rig go out on site, and we drilled to 14 meters depth, 14 meters of loess at this site. And that was put it back to be dry. We do see after rainfall water quickly accumulating in the valley and coming out, and quickly coming into the surface water system. And I guess that's implications there for water quality in terms of, this is a quick flow path for getting stuff on the land, soil particles or whatever's on that land surface quite quickly into the nearby river. I think it has implications for groundwater recharge, and it also has implications for things like irrigation management and the like. So, this is a work in progress. We're probably year 2 and what I hope will be a 5-year study. But I think the loess and the downlands is having an impact on groundwater recharge. We are using existing landscape evolution conceptual models to further our understanding, but we are also trying to use the existing information to outscale that study to different parts of to the South Canterbury. There are definitely opportunities here to collaborate with different people or students' projects. We have actually in the basement of this building all the core from those sonic rigs. I think there's probably a story to tell in some of those cores, and it'd be great to see someone kind of do more with it. All right, so you'll notice the branding's gone, and I guess this last little section, I just kind of wanted to talk about groundwater hydrogeology and visibility and the management of it. Earlier this week, I did a word search of the Resource Management Act, and I found rivers coming up 121 times, fish 25 times, wetlands 3 times, and groundwater was there once. And it wasn't actually groundwater, it was underground water, and it was in the section about existing wells. In my opinion, groundwater is incredibly invaluable, and I think we could all really develop a very compelling argument around its cultural, economic, environmental, and social value. I think, Canterbury faces its challenges in terms of fresh water, undoubtedly, and parts of the New Zealand and elsewhere in the world, fresh water is under pressure, and I think we have a role to play in this, in making sure that we do the work and then communicate our understanding to people who are developing those policies and to making those decisions. But I think we also need to be mindful of that, this is really, it is an integrated system. It's not, I don't want to, exclude one part of the system for the rest. We need to think about, all parts of the hydrosphere and how they connect. They do operate at different scales, at different temporal and spatial scales, and we need to be mindful of that, and we need to make sure that other people are mindful of that, but we can't sacrifice one part of that system for another. And I'm going to end on this particular slide. This is a Whakatoki. I'm going to try to read this out, but my Māori pronunciation is terrible. Sorry, Kelly. So, ko te wai, te ora, uni, mi koto. Water is the life giver of all things. And I particularly like the last sentence. Water is the very lifeblood of the earth. Indeed, it is the essence of life. So thank you very much for coming out and listening to me tonight, and happy to answer any questions. Thank you.
And we have discussion here.
Sure.
But it's really, again, it's really nice to see all of you here, and especially after the lockdown, where everyone was kind of a separate or isolated island, and now we are getting to connect together. And I hope that we'll have so many other opportunities to do that. To be fair with our colleagues online, I think that we should take one question from the floor here and one question from the colleagues online. So let's start with the floor here. Anyone that would like to say something or have question to Matt, or just general point to share with everyone else?
I'm relatively new to this. I'm a geologist, yes, but not involved in hydrogeology. Where do you get the funding from to do this kind of work? What's driving it? Is it always resource consent type stuff, or do you have government money independently to look in the ground?
Yeah, good question. So we get a range of sources. So for this latest study, at the moment, because it's a collaboration between a group of people, Environment Canterbury is putting up some money, and that comes from ultimately the ratepayers. But the other people involved, you know, NIWA, Plant and Food, and the like, they've also been stumping up some cash. To extend this particular project, we've just recently put in an application for MPI to seek some more funding for that, and hopefully we will find out in the next 2 weeks if that's successful. But so for projects like that, it's a real mix. For a lot of the stuff that we do day to day in terms of kind of resource management at Environment Canterbury, a lot of it comes out of general rates money. So part of my job is to provide advice to other people, and whether that's consent planners or compliance officers or the policy team, they need certain information to make those decisions, and we have our own independent budgets to go out and make sure that we're investigating some questions that are most relevant and useful to them, and that generally comes from rates.
Yeah, the generally find responding to things rather than being proactive.
Yeah. I think we've just kind of come out of a large sustained period where we're providing advice to planning people through the CWS, and that in a lot of the ways that was very much reactive. So we're now in a position where we can kind of see the pressures, and we're trying to get ourselves in a space where we can get ahead of the game, make sure that we've got that information in there and available before we need it. But it's a challenge because we don't have unlimited resources, and we need to make sure that we're spending money wisely.
Questions?
Sure. So from Kelly, hi Kelly. Have you got any thoughts on how we can get greater profile for groundwater policy, resource management systems and conversations? That's an awesome question. Do I know though? I think things like this are a start. You know, I think making these statements to people and making sure that people are aware that geology is out there and that it's a really vital part of what we do, our economy, of our drinking supplies. I think that's part of it. But I think there is a part to be said to be around making sure that we inform, local governments, regional governments, and central government. And I think my observation is that MFE and some of the kind of central government they are very focused on the surface water world. You know, you look at the MPSs, some of the freshwater documents, and they talk a lot about kind of freshwater values, and that's great. And I'm not saying that that's not what we should do, but there seems to be an absence of detailed information around groundwater, and I think that's problematic. And I really do think that some of the challenges that we face, we need a groundwater face for.
In your Lewis study, we considered that the rapid outflows are not so much a function of the Lewis wettability and as such, and more in the fact that there is a pervasive fracture network, and that the fracture network makes available downslope runoff irrespective of what the materials are. If you're on a flat surface, you're looking at Lewis on a flat surface, that movement would be vertical. So the characteristics that you described, the function of the fracture network is demonstrated rather than the Lewis character.
It may well be. It might be, and I think there's actually multiple things that are driving this. I think topography, just general topography, is having a role here. I think, you know, the physical characteristics of those soils, and I think in terms of what you're talking about, the fracture networks and the ability for water to kind of percolate down that way, I think that's important too. I'm not saying that I fully understand this. In fact, I don't. I think there's a lot of work that we could do here to understand these soils. You know, we haven't yet kind of crunched those numbers in terms of the water balance of how much water is coming in relative to rain and irrigation versus how much is going out that valley floor. It's just, in my mind and my gut, I suspect it'll be a fairly high percentage. And why is that? I think, you know, there are other studies that have been done, and they had looked at kind of vertical profiles, and the conclusions they kind of ran to is that at some point in the subsurface, and whether that's a fragipan or some other kind of feature, it seems to start preferentially flowing downhill. The dynamics of these systems are really interesting. So my colleagues at the Plants and Food have put in runoff plots, and basically they're measuring how much water falls and how much is running out the side. And it seems to be infiltrating at the top and quite a lot of water coming out at the different levels. And whether that kind of backs up what you just said, or whether it's a whole range of factors, yeah, I'm not sure. Did I actually answer your question? Maybe.
Got time for another 2 questions. So if we take one from online.
So is there any reason that you didn't use a lysimeter for the infiltration study? Yes, they're expensive. And mainly it comes down to cost. When we started up this project, we didn't have a huge amount of money to kind of spare. We work in informal collaborations of hydrogeologists and civil scientists. We had very discrete amount of money. What we had at our disposal were kind of the soil moisture balance. Would a piezometer be really useful? Yeah, but to what depth do you go down to? I guess this is 14 meters of Lewis. Do you need to have a lysimeter going down that whole soil profile to get an understanding of the drainage? And if so, that's more money than I have. I think it would be incredibly useful, but I just think it's slightly impractical on this side.
One more question from the floor.
dynamic. We use DPSA, which is deep penetration super heavy. So you're actually playing giant scale. And we were picking up the different lowest layers and Littleton fine water.
Okay.
And it was really good because just all of a sudden it's soft. And if you just separate it in a good pattern, you can actually find how water's flowing pattern.
Okay.
Yeah.
Okay. Oh, awesome. Maybe we can chat.
One last question from
Sure.
online, and then we will wrap.
It was well done with the question online. So, thank you.
Let's put our hands together to thank I think that I really happy to see here that we have so many as well as so many people have started his career as student and to see where he's got now. So I think that together we will do a good job and our interaction will just benefit every one of us. So thanks again for everyone that joined us online and also in person. If you have any further questions, please email them to me or to Matt, and we'll try to answer them in one single email. After we finish, we're going across the road for drinks. Stantec is buying the first drink, so these will get us the first drink from the bar. So if you follow James, sorry for volunteering you, James. This is James, my colleague in Stantec. Yeah, and he'll take good care of you, and I'll join you after we finish rearranging the whole. Thanks again.
Awesome. Thank you.